Assalamu alaikum wa rahmatullahi wa barakatuh. This is a part of engineering optimization course. Today we are going to discuss multivariable optimization with inequality constants. This is actually a continuation of the Lagrange multiplier method. So in the Lagrange multiplier method, we dealt with optimization problems with equality constants. So the inequality constants is actually the topic is related to the Kuhn-Tucker condition. So we are going to see how we can apply Kuhn-Tucker condition on optimization problems that involve inequality constants. So let's begin with the formal definition that we are trying to minimize a function fx. So our objective is to minimizing fx and subjected to the condition that is given constant that is given is g of jx lesser than or equal to 0. So this is ideally, we assume it to be lesser than or equal to 0. But this condition, if it is reversed, then some related condition will be reversed as well. The inequality condition, because of the inequality condition, we cannot apply the Lagrange formula. So if we want to use the same Lagrange formula on this one, we have to somehow convert this inequality condition into an equality condition. Okay, so that is why we, with this inequality condition or constant, we add some additional slag variables. Okay, so yj is a new set of variables, vectors, basically y1 to ym, column vector. So after the addition of that one, our inequality condition now becomes a equality condition. Now this problem can be, in this problem we can apply the Lagrange multiplier method. So first thing is to find out the Lagrange function. So we write the function as a Lagrange function in terms of fx and in terms of capital Gj, which is a function of previously it was x, now addition of your y. And also the lambda is nothing but the Lagrange multipliers vector. So for finding the stationary point, we have to go through the first order partial derivative in terms of x, in terms of lambda, and these two are available in your Lagrange multiplier method. And because of the introduction of the slag variable y, now we also have to have this one. So eventually this will help us to generalize our condition, first order necessary condition. So as you can see here, the first equation, that is equation 2.62, we have n number of equation and n number of unknown, that is x1, x2, up to xn. So in the second equation, we have n number of m number of equations. Third equation we have also m number of equations. So total equation, as you can see, is what we have is n plus twice n. And how many unknowns? X is n number of x. Okay, and you have a lambda, which is n, and also we have y, which is also m. So basically, variables are also n plus twice n. So n plus twice m unknowns and n plus twice m equations. So we should be able to figure out a solution out of this one, and we call this solution to be, we assume this solution to be our optimum solution vector, which will give us x star, then will give us lambda star as well as y star. Okay, now the equations that we have used in the previous slide, those are very, very important. And as you can see, these two are actually, this equation is nothing but our constraint. So g of j is being ensured in this equation. And the third equation, what we're doing here is, you can see that there is two conditions. So either lambda j has to be equal to 0, or our yj has to be equal to 0. Now, once the lambda j equal to 0, then that particular constant is not active, or we can say this is as a inactive. Okay, and where your yj equal to 0, that means in those cases, the summation of the yj and gj has to be equal to 0. So if gj equal to 0, that actually signifies that our gj will be 0, or with yj being 0. Okay, so these ones are actually active constraints. Okay, so we can have out of the m constraints, out of m constant, we can say that j number of them, which is a subset of j1, is active, we can assume. And the rest of the j is a subset of j2. So j1 and j2 can be equal to m. We are actually inactive. Okay, so this is what we assume. And since we are only concerned with the active ones, so we can rewrite our equation 2.61, which is basically partial derivative of your L with respect to xi. So that can be simplified into this one with only considering the active constraints. And also our second condition that was given 2.63, which is basically your d in the partial derivative of L with respect to lambda j, which is nothing but g of j x y, and which can be now divided into two segments, because one segment is subjected to your j1, where j is a subset of j in j1, and the other one, and this is actually active one, and the other one is inactive one. And for solving, basically we are more interested about the active ones, but at times it's difficult to find out the active ones. So we basically go for a generalized formula where we try all the conditions and all the circumstances, and based on that, whether active or not, we apply those conditions and we go through a validation process, which we have to omit, and based on that, we find out the solution. So math problem is relatively easier than this theorem that we are discussing here. So now, how many unknown and how many equation have? There is no doubt there is an equation here and an unknown here. Here, out of the m, you can assume that p number of them is active. So rest of them, n minus p, will be inactive. So total equation then is becoming n plus p plus m minus p, ultimately n plus m number of equation and n plus n number of unknowns. So we can easily solve this one. Okay, so the last equation that we have used, this one, 2.65, from this equation, if we expand this one, we can write in this way and take the partial derivative of f in the other side. This is actually gradient. Okay, and we have p. The p of them are actually active, so we have just written in terms of p of them. And if we find out the collective, if we write this equation, that means from x1 to up to xn, if we expand this one, then we can write as the left-hand side as a gradient of the objective function. The right-hand side is your Lagrange multiplier and the gradient of the constraints, the active constraints. So, and also del v, del f, and del gj can be written in this way. Okay, now basically we want to figure out what condition actually is required for our particular, the stationary point that we are going to get out of these derivatives, what are the conditions that has to be validated so that we can say that our chosen point is a valid point or actually truly a optimum point. So for that, you can see from this one, this is a gradient of f, and p of them is difficult to comprehend. So that is why we are assuming that only two of them are active. So p, we are assuming that p equal to 2. Okay, so we are just taking two components. Now, negative the gradient, what does it mean? Gradient means is basically the where you have the increasing value of the function. So that is why we have deliberately taken the negative value of the gradient. So since it's a minimization problem, we want to minimize the value. So we are taking a negative gradient. So in the other side as well, they have tried to explain this in terms of a feasible direction. The feasible direction we already studied from the other book. So we are assuming that the direction through which this function we are moving is going to give us a minimum value. Okay, so we are going towards a minimum value. So it means that here you have a negative gradient. So here also you should have a negative gradient. So we are assuming that S to be a feasible direction at the optimum point. And now if we pre-multiply this equation with S transpose, which is our feasible direction, we can have a equation like this. And by definition, since the S is a feasible direction, so we can assume that this value has to have a lesser than 0. Okay, so negative gradient. So our values are actually reducing. So since these were lesser than 0, then this condition has to be, the lambda value has to be greater than 0. Otherwise, if this one is 0, lesser than 0, this one is lesser than 0, then it will be positive. So we cannot validate the reason. So this is why it is important to understand the theory, because in some problems, you are going to see that your constraints that are given is lesser than 0. And once this is lesser than 0, we assume that lambda j has to be greater than 0 based on this condition. Okay, so this is for a minimization problem. Of course, you have to keep in mind minimization. Okay, now here somehow if your constraints are reversed for the same minimization problem, so if your constraints are having something like this, then automatically, because to have a negative value here, so your lambda values has to be greater than 0. So it's not universal that lambda, what should be the lambda value of 0 for a minimization or maximization. It is actually linked with our values of the constraints. So the inequality conditions. So inequality, whether it is a lesser than or greater than. If the constraint is lesser than 0, then our lambda value has to be greater than 0. And if the inequality condition is greater than 0, okay, sorry, it has to be greater. So I have just written the same thing again. So just rectify the thing. So basically, if your constraint is greater than 0, then lambda values has to be lesser than 0. So this is the most correct one. So based on this one, so whether your problem gives this condition, then this will give you a minimization. And if your condition, the problem is given a condition like this, then this should be the correct values of lambda that we are looking for. So these are not fixed. And in both cases, the opposite one will give you a maximization. Like here, we'll be looking for a lambda j smaller than 0 for maximization. Okay. Similarly, here as well, we'll go for lambda j greater or equal to 0. Okay, so what you can say is that for the minimization, these two have a inverse relationship. One is if one is greater, and the other has to be lesser. If one is lesser, the other has to be greater. Okay, now based on the equation that we have figured out, based on the active constraints, the equation that we have figured out, that particular equation is basically known as Kuhn-Tucker condition. Okay, so this is our Kuhn-Tucker condition. And based on the mathematicians, those who have figured out, derived the necessary condition, it has been named after them. So these conditions, we already said they are necessary condition, but they are not sufficient to ensure a relative minimum. But for a set of problems, those were known as convex programming problems, for those, Kuhn-Tucker condition is both necessary and sufficient for global minimization. So in the convex problem, basically, there is no relative a minimum or saddle point. Whatever, if you have a minimum, that is always a global minimum. Likewise, if you have a maximum, that is a global maximum. So that is why that condition, Kuhn-Tucker condition, is basically a necessary and sufficient condition for problems with convex functions or convex programming problems. So now we can apply this formula once we know the active constant. Somehow, if we don't know which are if the set of the active constants are not known, in that case we have to go with a general approach. So basically, we have to test all of them, out of them, which one is suitable and the condition is satisfied. We have to apply that. So this is what we already know. So it is nothing new. From where this is coming, it is actually coming from this condition, that is twice lambda j yj equal to 0. So lambda j equal to 0 is inactive, and yj equal to 0 is your active. As we already explained, this actually ensures that since our g is being added with yj square to make it equal, and since already yj is 0, you can easily say that our gj will be 0. And now if you just multiply with that lambda, which is some constant value, lambda j, then we can get this equation. So ideally, we should have been only applying to the active ones, but since we don't know it, we'll apply all the constant with all the lambda values with this equation. So one thing that is interesting is these two has been used for calculation, for finding optimum point, optimum, or we better say stationary, because of the fact that it may or may not be an optimum point. Okay. And the other two conditions that we have, which is nothing but your constraint as well as lambda values, which, as you can see here, in the opposite inverse relation. So one is greater, one is higher. So you have to keep in mind, if this relation is one of them is reversed, the other will also be reversed. So this is more or less for validation. So the first one is finding the validation. So first two is for finding the optimum point or stationary point, and second two is to validate or checking whether whatever the points we get, they are actually an optimum point or not. Okay, next thing is a constant qualification. So if you have a optimization problem that minimizes, or we generally say most of them are usually considered a minimization problem. But if it is optimum or maximized, just reverse in the procedure. Okay, so now minimization procedure, minimization problem with both inequality as well as equality constraints. So in this case, we include both of them, your lambda j as well as your beta k. Those are your Lagrange multiplier. Now you may ask why there is a negative sign in this one and why there is a positive sign in this one. This is how it is. You can take plus as well as minus. So in different books, they have used different uh, values for this. So eventually they give the same result. So maybe the points as well as in the conditions will be same whether you take it plus or minus, because of the fact that it's up to you how you define. Now, based on that, sometimes your lambda values will also be plus and minus, and that will be reversed as well. So this is this equation 2.77 is basically the Kuhn-Tucker condition, more generalized one because you are having both of them now, inequality constant as well as equality constant. And this is, if for equality condition, this equation is enough. For inequality, we have additionally this one. So these two will be now for your calculation, and the other three will be now for your validation. And your validation or checking of whether our obtained stationary value is stationary point is a valid optimum point or not. Okay, as we said, Kuhn-Tucker condition is necessary but not sufficient. So sufficient condition somehow can be related with this theorem, theorem 2.7. So it says that X star is a feasible solution of our minimization problem with both inequality and equality condition if the gradient of our inequality constant and the gradient of the equality constant. So inequality and equality constant, the gradient of them are linearly independent. Then you can say that whatever x star, lambda and beta we are getting, that will satisfy the Kuhn-Tucker condition. So combinedly, this one says that if the inequality constraints, gradient of inequality constant and gradient of equality constant, they are linearly independent. They cannot be one cannot be represented as a linear combination of the other. In that case, if we have a stationary point, that stationary point will basically satisfy the Kuhn-Tucker condition. So in other sense, we can say that this will give you a valid optimum point. So this linear independence is basically known as constraint qualifications. If the constraint qualification is violated, then we are not sure whether obtained point is a solution or not. Okay, so we don't have any idea about that. And also one of the difficulties of obtaining the or verification of your constraint qualification is that you should have already the values of x star. So if you already know the x star, then you can just check using this constraint qualification whether they are giving you a proper optimum point or not. So these are the two characteristics we should have in a problem so that we can apply this constraint qualification. So first of all the inequality and the equality constant has to be linear. So this is one condition. And all the inequality condition has to be convex. That means inequality condition function has to be convex. That means if something like this. So global minima, a relative minima is always a global minima. and your equality constant has to be linear. So if these two conditions are fulfilled, then if you have such x values, those x values will, and those x values also in the feasible zone, and then we can say that our that particular value of x tilde is basically a optimum point for our given problem. So this theorem is slightly difficult to apply because of the fact that you should have solved for the stationary point before applying the theorem. So this is inherent that you have to solve it. So example 2.13, it's a minimization problem. Two given constraints are given. Okay, so what they are saying that determine whether constant qualification and the Kuhn-Tucker condition satisfy the optimum point or not. So optimum point is not given. So you have to figure it out. So they have already figured out from the diagram. Somehow in the exam hall, either you have to figure out the diagram, and based on that, you have to figure out a suitable optimum point. Okay. So now, since they already have an optimum point, so they have to find out the gradients, all the gradients. And in this case, both the condition has inequality, so no problem with that. We'll figure out the gradient of that at the stationary point. We see that one of them is 0 minus 2 and another one is 0, 2. So we can easily write one as a linear combination of the other. So gradient of G1 x star can be written as minus gradient of G2 x star. Okay, so since we can write as a linear combination of this one, so you can see that they are not linearly independent. So our constant qualification is not satisfied for this optimum point. And additionally, if you want, you can also find out the gradient of our objective function at the obtained stationary point. So now, definitely the constraint qualification is not validated, but we can also check for the Kuhn-Tucker condition. So Kuhn-Tucker condition, if we apply in terms of, then as you can see, the first condition, which is basically coming from the LL by LX, and if you apply that one, and apply your x equal to x values are 0. So if you apply that, you can write in this way as a vector. So if you find out the x values, then as you can see that first condition is minus 2 equal to 0, which is not verified. So since this condition is not verified, not satisfied, even though others may satisfy based on different values of lambda, it's not. Once one condition is violated, no need to check for the other condition because all of the condition has to be satisfied. So neither our constant qualification is satisfied, nor our Kuhn-Tucker condition is satisfied. So this is one of the simplest problem with our Kuhn-Tucker condition. It says that a manufacturing firm producing small refrigerators has entered into a contract to supply 50 refrigerators at the end of the first month. So basically they are producing 50 refrigerators for the first month, at the end of the first month, 50 at the end of the second, 50 at the end of the third, and each unit is cost is this. X units cost is this. So the firm can produce more refrigerators. So even though they have to supply 50 at the end of the first month, 50 at the end of the second month, 50 at the end of the third month, but what they can do is they can produce more. So whether it will be wise to produce more or not, that is the question basically here. So if you produce it before, and you have to hold it for some time, then you have to pay 20 units per $20 per unit. So this is actually for storage or holding money. So this is manufacturing or production cost. This is your holding cost. So we have to determine how many we have to produce in each month. So we can say that X1 is produced in the first month, X2 is produced in the second month, X3 is produced in the third month. So we have to find out the values of X1, X2, and X3 so that the total cost, which is the summation of the production cost and the holding cost, has to minimize. The answer to this problem is actually quite simple and logical. Without solving anything, we can easily say that this total cost is just the production cost if you don't hold anything. So if you just drop this one, then this should give us a minimum value. Then we only have the production cost, which means the X1 should be 50, X2 should be 50, and X3 should be 50. So this is common sense logic, and we don't need to solve it. But the importance of this problem is this problem actually gives you the essence for how to actually construct the problem and how to deal with it. Okay, so you production cost of the first month, production cost of the second month, production cost of this third month, then the holding cost. So if you're producing X1, you are selling 50, so the rest of them you're holding. So this is the risk holding after first month. So, and holding after second month is this one. And after simplification, this is your objective function. So we have to minimize this objective function. Okay, so, and how to find out the constraints? Now, whatever you're producing and you're selling, so after selling, it should be greater than 0. Now, just be careful. Here, G, Gj, you can say 1, 2, 3 is basically greater or equal to, but in the problem we defined, we actually assume that Gj is lesser than 0. Since it is reverse, and on that case, our lambda j was greater than 0. So since all the conditions are greater than, so whenever we are looking for the lambda values, we should be looking for lambda j to be lesser or equal to 0. Okay, so whatever you're producing the first month minus whatever you're delivering the first month, that has to be, and maybe it may be 0 if you are producing 50, you are sending 50. So, or it can be higher, so it cannot be lower. So this is your condition of the first. So similarly, condition of the second is also same. Production of the 2 month minus the delivery that you have to give, and production of the 3 months, and the amount of the refrigerator that you are delivering. So these are the 3 constraints, and which are greater than. So our lambda value has to be lesser. So Kuhn-Tucker condition, for that, first thing you have to do is find your L. So even though they have solved in this one in certain fashion, but basically will not follow this approach. Rather, there is some simplified approach that are available in the internet. So we'll try to take one of them instead of this one. Even though if you are taking this one, it's good to go. So you can easily use this one. So basically, we will follow a step-by-step procedure like forming the L, that is fx plus lambda j gj. Okay, so summation sign, of course. So, or you can take one at a time, lambda 1 g1 plus lambda 2 g2. So this is how we're going to form the L. Then we're going to differentiate with respect to x, then with respect to lambda. So this is how we're going to approach to our problem. Okay, a more systematic way. But let's explain this one. So they just find out the condition here, and based on this condition, because we have 3 variables x1, x2, and x3. So these are the 3 equations that we obtained. And this is your lambda j ij. which came from two lambda j yj conditions. So here also you have three conditions. Lambda will be 1, 2, 3. G will be 1, 2, 3. So multiply these three you are going to get. And finally, your G greater or equal to 0 Gj. So that will give you these three conditions. And lambda values, we know that those since G's are greater than 0, lambda value has to be lesser than 0. So these are the three we can see. Now, as you can see, from it can be, they have also said that it can be, the solution can be found in several ways, but whatever the way you take, it will give you always a checking of all the condition. In this particular case, since you have three constraints, so you will have three lambdas, and basically you will have a combination of three parameters. So maybe all the lambdas are 0, maybe one lambda is 0. So basically this will be your condition like this. So these are the total 8 conditions you are going to get if you are solving in terms of our method, which is a generalized approach. But in this, in several ways you can do it. You know, whatever the way you pick, you'll always see there is a 8 condition to be checked. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what they have done is they have started with this condition. Okay. So they pick this condition. So either lambda 1 should be 0 or x1 minus 50 should be 0. So with lambda 1 to be 0, they have figured out the final equation, and then from the final equation, they have find out 4 conditions. So from each of the cases where lambda 1 equal to 0 or your x1 minus 50 equal to 0. So they will have 4 conditions. So in total, 8 conditions you have to check. So whether you check lambda values, lambda 1, lambda 2, lambda 3, or you start with one of the condition, okay? Not necessarily you can have to take this one, you can also take the other equations as well. So bottom line is all 8 scenario you have to check, and out of that, the one that will give you the conditions, that is x1, x2, x3 is 50 as we predicted earlier, and also the lambda values has to be lesser or than or equal to 0. So these two conditions validated. So we can say that our minimum cost will be achieved when we produce the required amount of each month in required amount in each month. That means we are not holding anything. So that holding money is being saved only. Okay, so this is one of the way, but this is not the way that we are going to follow. Rather, we are going to follow a more systematic approach that will make things a lot easier than this. The last topic of this one, which is not covered in detail, but in future class, we'll be covering the convex programming problem. So an optimization problem is called a convex programming problem if the objective function and the constant function, all the functions are actually convex. In that case, we call it convex programming problem. The definition and the properties of the convex functions are given in the appendix A. So if you want, you can have a look at that one, but we'll cover this one in detail, inshallah. Okay, so if you know your constraints, then you can form your Lagrange equation and solve this one. And as I said, that for this category of problems, your relative minimum is always absolute minimum, because in case of your convex function, there is no saddle point or relative minimum. So what you have is always the absolute minimum point. Okay, so more on this, inshallah, in the next class, in the future class. So this is all about your Kuhn-Tucker condition, or the optimization problem, multivariable optimization problem that comes with inequality condition, or both equality and inequality condition. And generalized case of the Kuhn-Tucker is also been discussed. Yeah, well, where we have discussed the constant qualification. So in the next class, inshallah, we will solve a few problems, maybe a small short class we can take on a few problems so that we can have more comprehension on this topic, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.